Hello students, we have discussed about the molecular orbital theory in the previous video, how the atomic orbital combine to form molecular orbital under the specific circumstances, and we have discussed about the combination of atomic orbital to the formation of molecular orbital. Let's recall it. When one s orbital combined with one p atomic orbital. Suppose we take this as an axis key, this y, and this is a z axis. So px orbital, when undergoes to addition overlap, that is called the plus plus overlap. We have already discussed about how the atomic orbital, their waves are combined, means linear combination of atomic orbital, and this will form two types. When plus plus overlapping takes place, means addition overlap takes place, and one the way of overlapping is subtraction overlap, in which plus minus overlap takes place. So in this way we have two molecular orbital formed. We will, from the two atomic orbital, two molecular orbital will be formed. So this is the s orbital, this is the s orbital, this is the p orbital. So student, we write here p orbital, p orbital. So formation of two types of molecular orbital takes place, one sigma and another anti-bonding sigma. So sigma orbital form like this, one bigger lobe and one smaller lobe takes place. This is called the sigma bonding molecular orbital, and it represented by sigma bonding, in which one s and one p atomic orbitals are involved. So similarly, when this s and this p orbital undergoes to subtraction overlap, means plus minus overlap. So another molecular orbital form is called the anti-bonding molecular orbital, like form this types and these types. So this is called the sigma anti-bonding molecular orbital, and this represent by sigma and one star here. So it is called the sigma anti-bonding molecular orbital. So it is also formed by the combination of s or p atomic orbital. So wherever the s and p two atomic orbital undergoes to this type of overlap, either constructive overlap or either destructive overlap, so formation of two molecular orbital takes place. One is bonding molecular orbital, and other is called anti-bonding molecular orbital. And in the previous video we have already discussed about the energy related to the bonding or anti-bonding. Students, as we discussed earlier, कि bonding molecular orbital has less energy than the anti-bonding molecular orbital, because whenever the bonding molecular orbital form, there is a less repulsion takes place, though, so their stability becomes more. Next we discuss about the combination of pp orbital, internuclear axis, combination of two p orbitals, like one and like another. This is the px, this is also px. So if plus plus overlaps takes place by combining two atomic orbital, if plus plus overlap takes place, means addition overlap takes place between the two p atomic orbital, so the formation of this type of atomic orbital formed. This type of atomic orbital forms. So it is called the sigma bonding molecular orbital. This type form when two p atomic orbital undergoing to plus overlap means addition overlap. So formation of this type of sigma bonding molecular orbital takes place, and it is represented by sigma bonding molecular orbital. So it will form X, so it is also called sigma px. Sigma bonding X px orbital. And if subtraction overlap takes place between this one addition and one subtraction overlap, plus minus means destructive interface subtraction overlap takes place. So the formation of this type of molecular orbital takes place. This type of molecular orbital takes place. So students, this is the place where the no electron present in this position, and it is called the sigma anti-bonding. Why it is called sigma? Because overlapping takes place at the internuclear axis. Sigma anti-bonding. Sigma anti-bonding molecular orbital. Molecular orbital, and we represent by sigma this type of a star, and this is the X. So overlapping of two px orbital takes place, either addition or either subtraction. Two ways of overlapping takes place in the linear combination of atomic orbital, and two molecular orbital will be formed with the linear combination of atomic orbital. One is called bonding molecular orbital and another is called anti-bonding. Which one will be called bonding molecular orbital, which is formed by the addition overlap, and which one molecular orbital will called anti-bonding, which is formed by the subtraction overlap. So in this way we can represent the bonding molecular orbital by simply sigma bx, and anti-bonding by putting the star on it. Let's we discuss about the linear combination of p, y and p z atomic orbital. Which type of molecular orbital will be formed? So if we take this type of this is 2 pz orbital, 2 pz orbital, plus minus indicate the crest and draw only. So if plus overlap takes place, plus overlap or constructive interface takes place, so the formation of molecular orbital form like this, one and another nodal plane and another like this. So this is the nodal plane. So it is called the bonding molecular orbital. It is called the bonding molecular orbital, and it indicates by pi because side-wise overlapping takes place. So whenever the side-wise overlapping takes place, the formation of pi bonding takes place. So one molecular orbital is formed by plus overlap and another formed by the subtraction overlap, means plus minus overlapping of this orbital. This will form like this. And this is the nucleus, and this is the nucleus. Here is the nucleus, and here is the nodal plane. It is a nodal plane. So student, it is called the pi anti-bonding. Anti-bonding is represented by the star, and it is called the pi anti-bonding molecular orbital. And in this way you can prepare the formation of molecular orbital by linear combination of atomic orbital when the SS combine, when the SP combine, when the PP combine, or when the sidewise PP combine. So different types of molecular orbital will be formed. Comparison between the sigma and pi anti-bonding molecular orbital. So sigma molecular orbital formed by whenever the atomic orbital combination takes place in the internuclear axis, and pi atomic orbital or molecular orbital form when the sidewise overlapping takes place. Write down the condition for the combination of atomic orbital. What are the condition for the combination of atomic orbital? So write down the condition for the combination of atomic orbital. First, the combining atoms combining atomic orbitals must have comparable energies. And next one is the extent of overlapping must be large, so the strong bond will be formed. And third one, the combining atomic orbitals have same symmetry. Orbitals have same symmetry about internuclear axis. These are the combination for the combination of atomic orbitals, so that the formation of molecular orbital takes place. Let's discuss about the energy level diagram, like the as we study about in structure of atom, Hund's rule or of Wow principle, the increasing order of energy of atomic orbital. See, same the rule follows here. So increasing order of molecular orbital. So at first we write down the lower energy atomic orbital. So sigma 1s, then sigma anti-bonding 1s, because anti-bonding orbital has more energy than the bonding molecular orbital. So students, like this, then 2s, and then sigma 2s, then sigma anti-bonding 2s, then sigma 2px, this x-axis, then we pi 2pz and pi 2py, then pi anti-bonding 2pz and pi anti-bonding 2py. These two molecular orbitals have same energy, so it is written in this form. And at last, much more high energy sigma anti-bonding 2px. So we take axis, then y, then z. So in this way, the all molecular orbital is written in the increasing energy form. So 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, and each orbital has maximum capacity to accommodate electron is only 2. So we write down the configuration at first, how the different electrons are filling. For example, uh, at first we write down the H2. So it has total number of electron is 2. So the configuration become sigma 1 s2. If we write down the H2 minus, so total number of electron is 3. So it becomes sigma 1s2, then sigma anti-bonding 1s1. And if we write down this type of species, so it has only one electron. This is the electron, one electron. So we will write sigma 1s1. So in this way, how many electrons are present in a given species, you can fill the electron in the increasing order of their energy. So student, so at first, electronic configuration of substance, electronic configuration of molecules, electronic configuration of a molecule. Suppose the molecule is stable when NB means bonding of electron becomes greater than anti-bonding. So in that case, we will say that this molecule is stable if bonding number of electron will be greater than the number of anti-bonding electron. And the second case, the molecules is unstable if bonding electron is less than anti-bonding, or the molecules is unstable if bonding equal to anti-bonding. So in this way we can find out the given molecule is stable or not. So, and next, bond order. How can we find out the bond order of the molecules? So it may be defined as half of the, we can write down the half of the number of electron in bonding molecular orbital minus number of electron in anti-bonding molecular orbital. So in this way you can find out the bond order of given molecule, NB minus NA. So you can find out the bond order of the given species. Bond order 2 means it has 2 double bond. Bond order 3 means it has triple bond. Bond order 1 means it has 1 single bond. In this way you can find out the bond order of different molecules. The bond order conveys the following important information, students. If the value of bond order is positive, it indicates a stable molecule, and if the value of bond order is negative or 0, it becomes the molecule is unstable and it is not formed. So by the value of bond order, if bond order becomes positive means molecules is stable. But if the bond order is negative or 0, that means molecule is unstable in nature or not found or not found. So on the basis of bond order we can find out the stability of the given molecule. So let's we discuss about the simplest molecule, hydrogen, at first. Suppose we have hydrogen, and how many electrons? Only 2 electrons. So we write down the configuration 1s2 simply. So how can we find out the bond order? Bond order means NB bonding minus anti-bonding by 2. How many bonding? So 2 bonding electrons. Anti-bonding, no anti-bonding orbitals contains electron, and by 2, so it comes 1. So what is the bond order of hydrogen? It is 1. It becomes positive. So this means single covalent bond, no unpaired electron, and number of unpaired electron indicates the magnetic character of species. If unpaired electron means it is a paramagnetic. If no unpaired electron means all are paired, that means it is called diamagnetic. So it has no unpaired electron means the magnetic property of this particular species is a diamagnetic because it has 2 electrons and pair of orbital. So another diagram, molecular orbital diagram, by way we can represent. Suppose this is the atomic orbital of hydrogen. This is 1s, or this is hydrogen, 1 hydrogen, and this is also 1s, and this is 1 hydrogen. So it is 2 hydrogen atom combined to form H2 molecules. So 1 hydrogen atom combined 1 electron, 1 hydrogen atom combined 1 electron. So when the atomic orbital combines, it forms 2 molecular orbital, students. So it has 1 sigma bonding, sigma 1s, and it has 1 sigma anti-bonding 1s. So in this way it forms 2 types of molecular orbital. This is the 1 atomic orbital, this is the 1 atomic orbital, and these 2 atomic orbital undergoes the linear combination. So 2 molecular orbital form by addition overlap, sigma bonding molecular orbital form, and by subtraction overlap, sigma anti-bonding molecular orbital form. So by the configuration we write the configuration of this H2 molecule, sigma 1s2. So both the electrons present in this sigma 1s2. So no any electron present in anti-bonding, so we write here 0. 2 electron present in bonding, so we write 2 and divided by 2. So we can find out the bond order of this electron. So in this way we can find out by representing this particular molecular orbital theory, this diagram, we can explain their property like bond order, their magnetic property, their stability. So many properties we can explain by the configuration or by representing this diagram. So let's we discuss about the another like way. Number 1, number 2. Suppose we have H2 plus. H2 plus means how many electrons it has? It has only 1 electron. So sigma 1s1. So if configuration comes sigma 1. So at first we find out the bond order. Student, bond order means bonding minus anti-bonding by 2. How many electrons in bonding? Only 1. No electron present in anti-bonding, so 0, and by 2. So the value comes half, means 0.5. So at first if we find out the magnetic property, there is 1 electron, so it is called the paramagnetic. because it has one unpaired electron. It is called the paramagnetic. And half bond order, that means its stability is less than the H2 molecules. And how can we represent, student? So right here, suppose this is 1s, only one electron, and another hydrogen has no electron. See, this is H, this is H. So two molecular orbital form, one will be anti-bonding and one will be bonding. So this is sigma 1s and this is sigma anti-bonding 1s. So how many electron it has, students? 1. So and 1 and OB sigma 1s. So it has only one electron in sigma bonding molecular orbital. So in this way you can represent the following or given species: H2 plus, H2. Let's we talk about the H2 minus. Suppose we have H2 minus, number 3, H2 minus. How many electrons? It has 2, and again we write like this: sigma 1s2 and sigma anti-bonding 1s1. So total number of electrons becomes 3. Mb minus Na. So 2 minus 1. 2 minus 1. Then value will come. Obviously, a value becomes half. Value becomes half. Mb minus 1a. Sigma 1s2, sigma anti-bonding 1s. So 2 minus 1 by 2. So we can find out the bond order becomes half. And what is the characteristic of magnetic property of this H2 minus compound? So see here, one unpaired electron present, so it becomes paramagnetic. Paramagnetic in nature. And how can we write the electronic how can we represent the structure of this molecule? So simply sigma 1s2 is filled here, sigma anti-bonding 1s, so filled here sigma anti-bonding. In this way you can represent by like this. So here is sigma 1s2 and sigma 2. So do practice and try to do simplest molecule at first. We will discuss another exceptional cases involved in this molecules. So students, in the next video we will discuss about the next example with in details. So try to do it. That's enough for today.